Hello students, this is Mr. McAllen and this is the first day of Unit 2 and we're doing the flipped classroom for this unit. So what we want to do is, in the first example that I'm going to talk about, we're going to be talking about finding the average rate of change of a falling body, and then the second example we're going to do the instantaneous rate of change of that falling body. Um, After we do that, we're going to examine the differences between them and talk about, in the second video to this unit, um, some basic limit laws and properties. And finally, in the third video, these videos should be about 5 minutes each. We're going to put some limit laws to work to solve some problems. So, moving right along, in our first example, we have a falling body that is falling from, it's falling through the air, and it's a dense body, so we don't have to worry about wind resistance effects. And the position, the distance that it travels, is based on this equation, 16t squared. So um, we want to find the average speed for the first 3 seconds. So that means we want to find out how far did it fall in first 3 seconds and find that average rate of change. So in that case, it's basically finding what the position was at 3 and subtracting from it the position at 0 and then dividing it by the time that it was traveling. So this is average rate of change, as you should know, is also known as just slope between points. So what we do is we evaluate the function at 3. Y at 3 is going to be 16 times 3 squared. Y at 0 is going to be just 16 times 0 squared. And when we get those values, that would be 16 times 9, which is 150, I think it's 144. And the other value is simple, it's a 0. So we're looking for a change in position of 144 minus 0 over 3 minus 0. And that will give us, and if we look at units, that will be in feet, and the denominator units will be in seconds. So our average rate of change is going to be 144 divided by 3, which will be 48 feet per second. Now, on a graph, if we were to graph this, we would look at average rate of change as being a slope between 2 points. So this is a parabolic shape. Say this is 16t squared, the equation. So at 3, we were at 144. At 0, we were at 0. And if you draw a secant line between the two, what we've just computed is the slope between the 2 points, the slope of the secant line. And this would have been 144, this would have been 3, and we would have come up with 48 feet per second. Now in our next example, we're considering what is the instantaneous rate of change at 3 seconds. So if we draw just a picture and we show that 3 seconds where it was 144, we want to talk about what the instantaneous rate of change is, or the slope of the tangent line. And we find that by forcing the time interval to become really, really small. So for instance, we're going to do the slope between 2.99 and 3. So this we may need a calculator for. So we'll just do the same general equation as average rate of change. We'll do y at 3 minus y at 2.99 all over the time interval from 3 minus 2.99. It's the same exact approach as before with average rate of change. The only difference is we are shrinking the time interval, making the average rate of change more instantaneous. So I'm going to need a calculator for this, so I'm going to pause the video while I bring the calculator up on screen. So I've brought the calculator up on screen. I've programmed in the function 16x squared, and I'm going to just use a table, or I'm going to use y1 to help me calculate this. So I'm going to go to alpha F4, and if we have a Texas Instrument calculator, we could do this. I'm going to plug in 3 and get its value. So that's 144 again. And then I'm going to plug in we're going to do the same operation with a smaller value of time, 2.99. I'm going to make my time interval really, really small, 2.99, and that's going to tell me that I'm at 143.0416. And then I'm going to divide it by the time interval of 3 minus 2.99 is a 0.01 second time interval, and we're going to see what our instantaneous velocity is. So I'll calculate that, and I'm just going to pause the video while I do that. Okay, so what I've basically done is I've calculated the difference, which is 0.9584 if you look to the left on the calculator, and dividing that by the time interval 0.01, we have a 95.84 feet per second instantaneous velocity. Now, we can shrink the time interval smaller, so what I suggest you try doing is change your time interval to even smaller, go from a 0.001 interval, so that would be and see what happens to your instantaneous velocity. Your instantaneous velocity is going to head towards a fixed value, and as the time interval shrinks and shrinks and shrinks, we get more and more instantaneous. Anyway, I hope this video has helped in understanding how to compare an average rate of change to an instantaneous rate of change, and there will be some problems in class that we do which deal specifically with this type of problem. Look for the next video where we'll be working with what a limit is. In the next video, we're going to go over what a limit is and how we find a limit graphically and how a limit pertains to this problem that we just did.